The topic we are going to discuss is on diagnosis and recommendation integrated system for identification of yield limiting nutrients in different crops. Earlier, what we used to do diagnosing the nutrient deficiency symptoms following the critical nutrient concentration or sufficiency ranges. So, the critical nutrient concentration is that the level of nutrient below which the deficiency of that particular nutrient will appear on the crop. Above the critical level, there will not be any deficiency seen. And sufficiency range means it ranges from, for example, 2 to 5, 5 to 7, like that. It is a range. Under that range, no deficiency symptoms are seen. Below that range, the symptoms are seen. So, like that, the critical nutrient concentration and sufficiency range tissue aging methods were earlier there. So the tissue aging generally it influences the nutrient concentration that, for example, concentrations of nitrogen, phosphorus, potash and sulfur tend to decrease with the tissue aging. As the age of the crop advances, the nutrient contents like N, P, K and sulfur will decrease. But in contrary to this, the calcium and magnesium concentrations they will tend to increase in the older tissues because of the low mobility of these nutrients. So the dynamic nature of plant tissue mineral composition depends upon, it tends to restrict the use of leaf analysis for nutritional diagnosis. So the criteria for critical levels or sufficiency ranges, it generally depends on norms for diagnosis derived from a specific plant tissue part and age, and it classifies based on the leaf nutrient concentration. So thus the plant growth stage for leaf sampling is an essential factor. It is very important for the application of the both the methods. So critical nutrient concentration and sufficiency range, as I told you, the plant growth stage for leaf sampling is essential factor for the application of the both methods, and therefore the diagnosis of on these criteria are usually applied in leaf samples obtained from the well-defined growth stage. Because for this purpose, the growth stage has to be defined, and which part of the leaf sample have to be sampled is to be defined for the different crops. Usual methods for leaf chemical analysis interpretation, it depends upon nutrient concentration comparison with the reference values. Just I told you the critical nutrient concentration or sufficiency ranges. So the chemical the analysis interpretation of the nutrient deficiencies depends upon the reference values. Below the reference value, it is called diagnosed as a deficient. So nutrient concentrations far below or above the reference values are associated with the decreasing vegetative growth, yield and quality. So not only the below the reference levels, it shows the deficiency, and above the more far above the reference levels also it shows the toxicity. So these methods intend to evaluate isolated deficiency or excess values without measuring the overall nutritional balance. So moreover, researchers related to the subject indicate a great difficulty in establishing consistent critical values and relate them with higher yields, mainly because the nutritional status varies with the leaf tissue maturation. So as the leaf age advances, the contents of the main important major nutrient elements will decrease. So thus sampling definition is a fundamental step for better accuracy of these methods. Annual crops, the established standard sampling period many times occurs too late in the growing season, so that fertilizer application will not be effective to correct a nutritional problem or may not match the sudden symptoms of the nutritional disorder. So, as we notice the symptoms, because the sampling period, if it is latter stage, if sampling stage to be taken is latter stage, by the time we analyze and find the nutrient deficiency, the correction method will pass on the growth stage. So it does not match the sudden symptoms of the nutritional disorder. So to overcome this problem, it would be necessary to get nutritional reference values for several maturation stages, and as a matter of fact some of these standards have already been established for a few crops. Later, the sampler should communicate this information to the analyst or person taking care of diagnosis so that appropriate norms can be selected or used. So not only some particular that latter stage of the growth to be defined, different stages. For example, one crop is there, vegetative phase, one reference sample, and maximum growth period one reference sample, maturity period one reference sample, so that as and when we find the any deficient, I mean deficiency and it is below the reference value, we can take up the correction measure at early stage itself. So for different crops, the already different critical levels have been established after doing so much research. There are critical levels established for the different crops. So on to, as on today. So the factors that affect the issue aging rate might also influence the relation between the nutrient concentration and maturation. An option of these diagnosis methods was proposed through the DRIS, that is Diagnosis Recommendation Integrated System. It was developed by the Bufils 1973, which defined that in general nitrogen, phosphorus, potash concentration decrease with the tissue maturation. So nutrient ratios. So earlier what we have done, taking into care of that particular nutrient, whether it is below the reference level, whether it is deficient, that like that we use it to take the correction methods. But there are some nutrients which do not show the symptoms on the crop, but there may be hidden hunger, reducing the yields. So later on, the nutrient ratios importance has been raised. So therefore, the ratios of nitrogen in relation to phosphorus, nitrogen in relation to potash, like that phosphorus in relation to potash, like that different ratios or reciprocal ratios and multiplication ratios should be kept constant. In the same way, because of concentrations of calcium and magnesium generally increase with maturation, coefficients between these nutrients should result in the constant values. So moreover, the product of two nutrients with concentrations running in opposite directions with time, nitrogen, for example, nitrogen, calcium, for example, also should remain constant. So the plant nutrient ratios can be used to assess the crop nutrient balance. Suppose nitrogen in relation to phosphorus, balance between the different nutrients is also important rather than the single nutrient importance. So for example, nitrogen phosphorus and nitrogen sulfur, potash magnesium, calcium plus magnesium with in relation to potash, like that in relation to the other elements, it is very important to assess the nutrient balance and deficiencies. So when nutrient ratio is optimal, optimal yield occurs unless some other factor reduces the yield. So when the ratio is low, a response to the nutrient in the numerator may be obtained. For example, some ratio is there. Suppose 5 by 6, for example, 5 is nitrogen, 6 is, for example, that the ratio is too low, for example. So that means that numerator value, the nutrient response to the numerator value can be obtained. So if the nutrient in the denominator is excessive, yield response to the application of the nutrient in the numerator may or may not occur. So when the ratio is too high, the reverse is the true. So optimum nutrient ratios are established similar to critical levels for different nutrients. Caution should be exercised in interpreting the nutrient ratios. So sometimes nutrient ratios also it makes complications. For example, when nitrogen sulfur ratio is 17. So there are three possibilities exist when both nitrogen and sulfur. Suppose they are optimal also, it shows same ratio. If both are excess also shows same ratio. If both are deficient also it shows the same ratio. So it does not reflect the which nutrient or nutrients are deficient or sufficient. So that three maybe possibilities are there. So there is a complication in identifying. So it is difficult to determine from the ratio alone which situation exists in the plant. So for example, when nitrogen sulfur ratio is more than 17, either nitrogen could be excessive or sulfur could be deficient, or a yield response to the applied sulfur occurs when if sulfur is the deficient. Whereas if nitrogen is high and sulfur is normal, the additional sulfur may dilute nitrogen in the plant. So alternately, if the nitrogen sulfur ratio is less than 17, either nitrogen could be deficient or sulfur could be high. So with low nitrogen, addition of the nitrogen may increase the yield. So thus nutrient ratios are very difficult to interpret and yield response is not always obtained when ratio is outside the optimum range and is to be integrated with the critical nutrient concentration. So I told you nutrient ratios and constants in situations with nitrogen and sulfur. For example, it is normal or it's optimal range. Also, there are three possibilities. For example, nitrogen is normal, sulfur is normal. One ratio is there. Suppose nitrogen is excess and sulfur is excess also, same ratio may come. If the nitrogen is deficient, sulfur is deficient also, same ratio may come. So it will not reflect whether particular nutrients are sufficient or deficient, even though taking into consideration the ratios. So here you see when the nitrogen sulfur ratio is either above or below the optimal range, two possibilities exist in each case. For example, nitrogen is more, sulfur is also more. If nitrogen is normal, sulfur is inefficient. And nitrogen is more and sulfur is inefficient, this is your nitrogen excess. So like that, different these ratios are not reflecting properly. So, because taking and studying all these aspects, particular reference levels, critical nutrient concentration and sufficiency ranges, and later on nutrient ratios, observing all those, the constants in identifying the nutrients through those methods, the latest method, that is diagnosis and recommendation integrated system, that is called DRIS, was it is a new approach for interpreting the leaf or plant analysis. It was developed by Bufils during 1973 at the University of Natal, South Africa. So of late, many scientists, they are using this approach to identify the yield limiting nutrients in the different crops, in particular the annual crops like horticultural crops. So it is a comprehensive system which identifies all the nutritional factors limiting crop production, and in so doing, it increases the chances of obtaining higher crop yields by improving the fertilizer recommendations. New interpretation for leaf analysis was first developed, as I said, it was proposed by Bufils 1957, and later on it is improved during 71 and 73. For rubber trees, it was evolved for rubber trees, named as the diagnosis and recommendation integrated system. So later on, this method uses the nutrient ratios. Uh, Later on, this method was extended to the different other crops. So in this method, what it is done, it uses the nutrient ratios instead of absolute or individual nutrient concentration for interpretation of the tissue analysis. Earlier, we have seen that nutrient ratios are there, but nutrient ratios not only here individual nutrients, not only here nutrient ratios, the nutrient one particular ratio in relation to the other nutrient ratios, it will take care in the DRIS method. So soon after the initial proposed DRS norms for leaf analysis interpretation were released, further more and ones were developed for further agriculture, forest, and horticulture crops also. So to develop a DRS, does it DRIS for a given crop, the following requirements must be met. So some factors we have to must define. So all the factors suspected of having an effect on crop yield must be defined. The relationship between these factors and yield must be described. Calibrated norms must be established. Recommendations suited to particular sets of conditions and based on correct and judicious use of these norms must be continually refined. So DRS method expresses results of plant nutritional diagnosis through indices, which represent in a continuous numerical scale the effect of each nutrient in the nutritional balance of the plant. So these indices are expressed by either by positive or negative values, which indicates that the referred nutrient is in excess or deficiency or respectively. For example, if the more the positive value, it is excess. If it is more the negative value, it is the deficient. So the positive and negative signs, it shows the either it is a deficiency or excess. So the closer to the zero or the indices for all the nutrients, the closer will be the plant to the adequate nutritional balance. The working principles for the DRS are mainly based on the ratios among nutrients are frequently better indicators of the nutrient deficiencies than rather than isolated individual concentration values. So some nutrient ratios are more important or significant than others. Maximum yields are only reached when important nutrient ratios are near the ideal or optimum values which are obtained from the high yielding selected populations. So the whatever the mean values of the nutrient ratios obtained in the high yielding populations, they will serve as the reference values for calculating the DRS norms. So the variance of an important nutrient ratio is smaller in a high yielding, that is reference population, than in low yielding population, and to the relations between the variances of high and low yielding population can be used in selection of the significant nutrient ratio. So the ratio, particular ratio in test sample in a particular ratio in the high yielding population and particular ratio in the low yielding population. The variance ratios, whichever the ratio is more, that particular ratio has to be selected for as a different DRIS norm. So the DRIS indices can be calculated individually for each nutrient using the average nutrient ratio deviation obtained from the comparison with the optimum value of the given nutrient ratio. There are different advantages over the other methods. It presents the continuous scale and easy interpretation. It scales, it is the positive to 0 to negative values. It shows the scale. Positive means sufficient, negative means deficient. So it allows nutrient classification from the most deficient up to the most excessive, as I told. So it can detect cases of yield limiting due to the nutrient imbalance even when none of the nutrients is below the critical level, and finally allows to diagnose the total plant nutritional balance through an unbalanced index. So an additional advantage of DRIs acknowledged by some others but reputed by others is that overall it is less sensitive to the tissue aging in comparison to the others. In this DRS approach, the plant analysis that samples are analyzed for nutrient contents and they are expressed as the ratios of the nutrient with others. So the plant samples, the stage of the plant sample, the index leaf sample, all those things are established for different crops. So that index leaf samples are to be collected at that particular stage, prescribed for that particular plant, and all the plant samples are analyzed for the different nutrient contents and they are expressed as the ratios of the nutrients with others. So all these nutrient ratios in relation to other nutrient ratios will be taken into consideration under DRS. For example, N by P ratio is there. So not only N by P ratio is important, the ratio of N by P in relation to the N by K, N by S, N by zinc, like that it comes in relation to other nutrient ratios as it will be taken into consideration in this DRS approach. So the ratios of nutrients in high yielders and low yielders will be compared and DRS norms will be derived and finally DRS indices are derived to identify the yield limiting nutrients. So as I told, first we have to establish the DRS norms and then we have to calculate the DRS indices. Depending upon the DRS indices value, we can define whether the sample is deficient or sufficient. So the approach is generally suitable for perennial fruit crops. As I told, this is long duration crops, perennial fruit crops. It is most suitable. But now the not only long duration crops, but also the DRS is coming up well in the short duration crops also, like soybean, wheat, and rice also. This is the provisional DRS chart. Either we can see this chart is prepared based on the mean reference values. These are the general reference values. For example, for sugarcane corn, it has shown one example that sugarcane corn that N by P is 8.2, N by K is 1.57, K by P is 5.2. So it is the reference values. So what happened? For example, here at the intersection point, this is the intersection point, for example, N by P is 8.2. So here intersection point, it started from 8.2. So it is increased 8.2, 9.43, 10.6, like that. So N by K intersection point is 1.7. So here it started from 1.57, it increased to 1.81, 2.04, like that. And K by P 5.39. So here it started from 5.39, increase to 6.2 and like that 7.01. So like that the values of the mean started from the intersection point. So these values as it these values are showed as horizontal values or suppose the value is within this lower circle, the nutrients are within the nutrients are balanced. So the values are within the inner circle of the chart. Horizontal means. So then it is diagonal means values. If the values in between this second circle, we can show as the diagonal values. That is downward or upward, like that we have to show. And out of these two circles, these are shown as the vertical for these values. So vertical symbols we have shown for values found beyond the outer circle. For example, this test sample, this is the reference values. For example, one sample we analyzed, we found that nitrogen 2.34, phosphorus 0.39, K 1.17. So the ratios of these, for example, N by P is equal to, that is 2.34 by divided by 0.39, it comes to the 6. For example, n by k. For example, n by n is 2.34, k is 1.17. So 2.34 divided by 1.17 will get 2. So like that, k by p. K is 1.17, p is 0.39. So 1.17 divided by 0.39, it comes to 3. So these are the three ratios possible in relation to phosphorus, potassium, K related to phosphorus. Because an excess of one plant nutrient corresponds to the shortage of the another. By convention, only insufficiencies are recorded for the purpose of diagnosis, and this is done stepwise for each function. Identical diagnoses are obtained by considering either excesses or insufficiencies of both. So as I told you, this is the horizontal symbols, diagonal symbols, vertical symbols are shown in these circles. So the chart is constructed for the three axes. I told you, depend upon the intersection, the mean values are taken. So the point of intersection of the three axes therefore represents the composition for which one is striving or at which one should achieve the highest yield permitted by limiting factors other than nitrogen, phosphorus, and potash. So the concentric circles can be considered as this is the confidence limits, the inner being set as the mean, inner being set as the mean. So the stepwise, then I'll explain about the DRS norms, how to calculate. The first step in DRS method is establishment of the standards or norms, and the same applies to the DRIS method. So the DRIS norms are always obtained in a high yielding population and named reference population, which is selected from the large population. So large number of population, samples to be collected and to be analyzed. So then we have to divide that yield populations, that is high yielding population and low yielding population. The mean values of the particular ratio of high yielding population is considered as the reference value. It is called as the reference value. So norms obtained from the large database derived from different soil types, climates, and cultivars will be considered representative. More the number of the population, the more the accuracy in deriving the DRS norms. The more the large number of samples, if we take, the accuracy of the deriving DRIS norms and diseases is more accurate. So DRS categorization of population. For the chosen population or database for norms definition should be subdivided into two subpopulations or categories. So the non-abnormal plants or reference population that are not influenced by adverse conditions and present yield significantly higher than an arbitrary established level. Those are called high yielder values. And abnormal plants or non-reference population influenced by other factors with lower yields than the established one are called low yielders. So the selection of the reference population is an important factor for the DRS's effectiveness and success. Walworth and Sumner during 1977-87 agreed that the reference limit to separate the two subpopulations should be arbitrarily chosen because each subpopulation ought to present normal distribution. So how to divide the population into high yielding population and low yielding population? What is the criteria has to be taken? So I will explain in the coming slides. Some others recommended that the reference population contain at least 10% of the overall database observations. Malvolta, for example, the authors Malvolta and Malvolta, both are brothers, during 1989 recommended the reference population to be obtained with 80% maximum yield observations. So how to select the DRS norms? DRIS norms are originated after the reference population definition. The relation between all the nutrient pairs and their respective standard deviations or coefficients of variations are obtained. So the ratio between a pair of nutrients can be direct or inverse. The concentrations of N and P, for instance, can be related either to be N by P or P by N. So it may be, it may be the direct ratio, the like N by P, or maybe reverse P by N. So different ratios will take into consideration, and one ratio will select depend upon the, coefficient of variation which is the depend based on the coefficient of variance ratio. So in DRS calculation, each pair of nutrients is discriminated by only one expression. So these are several criteria to select the best adequate expression, and the most used is the variance largest ratio among high and low yielding population. Just now I told you. So here one ratio only we would, for example, N ratios. For example, you take N by P and reverse the P by N. Another is the N and P. So among these three possible combination, only one ratio will be selected. One ratio will be selected. That the main value of that ratio is called DRIS norm. So initially, the DRS reference or norm values should be determined as already described for all the nutrient ratios or products used in the indices calculation. After norms definition, sample analysis results are ready to be submitted to the DRS indices calculation, which are composed of each nutrient individual index calculated in two steps. First, the functions of the each nutrient pair ratio, and second, the sum of the functions involving each nutrient. Hypothetically, A to N nutrient indices can be calculated. For example, depend upon nutrients. For example, we take 10 elements, 7 elements, 5 elements, like that. We will formulate the different ratios of the elements and will select one particular ratio for the particular one nutrient combination. So this is the calculation, the functional values we have to take into consideration calculating the indices. So the functional values are derived from the DIS norms values. For example, here the functional value, for example, A is one nutrient, for example, we take. So the function of A by B plus function of A by C, function of A by D, function of A by N. These are the nutrients. For example, B is one nutrient, C is one nutrient, D is one nutrient, like that. The index of A is function of A by B. A and A by C, A by D, like that, up to N number of nutrients divided by the Z means the total number of ratios we have taken into consideration, that shows the Z number. So like that, the B index we have to calculate for the B. So for example, this is A by B function value there. So B, if it is this is numerator and denominator are there. For example, this B is the denominator. I mean, so that what happens, we have to show the minus value. So like that, the minus and positive values have to be assigned depending upon the index value calculations. When A by B is the larger or equal to the A by B, for example, functional A by B, how we will calculate? There is a formula, A by B divided by small a by B minus 1 into 1000 by coefficient of variance. So what is the capital A by B? Capital A by B is the test sample, which we are going to identify the nutritional deficiencies of that particular crop of that particular field. Small a by B is the reference value, which that is the difference norm, DRS norms developed for that crops. So this is when the test sample value is larger or equal to the mean value, this ratio we have to take. If the test value sample is smaller than the reference value, this ratio, that is 1 minus small a by b divided by a by b into 1000 by divided by CV. So like that, we will calculate the functional values for all the ratios. These functional values we will substitute in this calculation and we will derive the test index value. So in these equations, A by B, the tissue nutrient ratio of that plant to diagnosis. Just now I told you, this is the test sample. Small a by b is the optimum value or the norm for that given ratio, that which we have developed, which we have derived that norm from the calculation. So then C, that is the value of that is the particular selection of that ratio, and that value of that ratio in high yielding population is the this norm. So C is the coefficient of variation associated with the norm. So Z is the number of functions in the nutrient index composition. So suppose we will take 5 values, 5 ratios divided by 5. If we take 6 values divided by 6. If we take 10 values divided by 10, like that. Depend upon the number of ratios we have taken into consideration for calculation of the DRS index. So values for those functions such as the function of A by C, function of A by D are calculated in the same way using appropriate norms and coefficient of variation. So one nutrient index is the average function of all the ratios containing the given nutrient. So then this indices, the components of this average value are pondered by the coefficient of variations reciprocal of high yielding populations. Those are the reference populations. So thus if the capital A by B, that is the test value ratio, and the capital A by C ratios are both used to generate the index for the A nutrient. The contribution of each one to the calculation of this index will be the function of the coefficient of variations values of the reference values associated with them. So what will reflect the relative influence of these two expressions in the crop yield? For example, how we'll calculate this indices, I will show in these coming slides and this slide. For example, we take maize crop, maize leaf sample nutrient concentration in the dry matter. What is it, for example, dry matter values you take, nitrogen is 3.3%. After analysis, we got these are the values: nitrogen 3.3%, phosphorus 0.20%, and potash 1.2%. So these calculations are to be made, or the ratios between the nutrients represented in the capital letters in the previous equations, that are, for example, N by P capital letters. That is, for example, so these capital letters, I told you these test sample values. For example, maize crop nitrogen is 3.3. For example, N by P, for example, that is N 3.3 divided by P 0.200. It gives 16.5 N by P ratio. So like that, N by K, N 3.3% divided by K, that is 1.2%. It gives to the 2.75. Like that, N by P, 1.2 divided by 0.2, it gives 6. N by P, N by P, N by K, N by P ratios are derived by taking into this nutrition contents values. The ratios of same nutrients in the reference population, that are those are the DRIS norms represented in the small, that is capital. That, for example, N by P is the test, small N by P, small pi is the reference sample. Reference samples are nothing but the values of the selected norm derived from the high yielding population. The mean value of the high yielding population of that particular ratio is called the reference value. That is called the DRS norm. For example, the selected ratio N by P, so the test samples, ratio is 16.5. So the same ratio, the reference value ratio is 10.4. So for the coefficient of variance related to this yielding population ratio is 14. So like that, N by K is the reference sample 1.49. Coefficient of variation related to this ratio of the yielding population is 21. So similarly, K by P, that is the reference value 6.74. This is its norm for K by P. And CV related to this K by P is 22. So then we have to calculate the functional values. For example, first we will calculate the function NP, functional value of the N by P. So if it is their functional value of the N by P, then what happened? So then earlier I have shown in the previous slide, because here the capital N by P, that is test value, is more than the reference value. If the test value is more than the reference value, you have to take the one equation. If the test value is the less than reference value, you have to take the other equation. So two equations are derived. For example, here the N by P is the 16.5, the reference value N by P is the 1.49. So the test sample value of N by P is more than the reference value sample of N by P 10.4. So then you have to take this formula. So capital N by P minus 1 divided by small n by P into 1000 by coefficient of variation. For example, capital N by P, either capital N by P means test sample, this is 16.5. So 16.5 here we have taken. Then the reference value, test norm value, that is small n by P. Small n by P here you see 10.4. So you divided by 10.4 minus 1 into 1000. So then the coefficient of variation for this ratio, 10.4, 10.4 is ratio. No, for that ratio, CV is the 14. So we have substituted 14. So then we calculate this way. Then we have derived 45.96. The 45.96 is the value of function NB, function of N by P. So like that, we have to calculate for the function of N by K, function of N by zinc, function of N by sulfur. Like that, different all functional values have to be calculated, depend upon the test value sample value and reference value sample. Taking into consideration different equations, we have to calculate the functional values. So in the similar way, I told you that different functional values we have to calculate, functional N by K. Like that, different ratios we will calculate. Here what happened? Okay. Like that here, functional n by k calculated. Like that, for all these functional values, we have calculated. For example, nitrogen index. We have taken into consideration only three elements. For example, we have taken into consideration. So earlier we have calculated here. Function n by p is 45.96. Okay. Then function n by k, here we have calculated, we have derived here by calculation. Here it is 40.27. So then how to calculate the nitrogen index? Nitrogen index. So nitrogen index value is the, for example, here nitrogen calculating. So nitrogen is upper side, P is lower side. So nitrogen, when we are calculating nitrogen index, if it is nitrogen upper side, we have to give the positive sign. If it is coming to lower side, that is, I mean, then we have to give the minus value. For example, here we will calculate the nitrogen index. Here we have taken two ratios, that is n by k, n by p, and n by k. N by P is the 45.96. Here n by K is the 40.27. So here we have calculated 45.96. This is n by P. N by K is the 40.27. These are the functional values divided by here. How many ratios we have taken into consideration? Only two ratios we have taken into consideration. So that's why divided by 2. So it gives the 43. So this is the nitrogen index value. DRS index for nitrogen is the 43. So similarly, we have to calculate for the phosphorus index. So here what happened? Phosphorus index means here phosphorus is the lower side. Upper side is nitrogen. Then we have to, if it is lower side, we have to give the minus negative assignment for this functional value. So here what happened? Here also negative, lower side. Then we have to give the minus value. If it is upper side, we have to give the positive value. So like that, we have to assign the positive or minus values. Then here the n by p value, we have taken 45.96, we have to give the minus value. And similarly 40.27, this is the phosphorus index. Of course, it is n by k by p value, it is not here given, that you have calculated the 5.6. So two ratios, it gives to -20. Similarly, k index. So n by k value here is 40.27 and divided by the k by p value 5.6, and it gives -23. So the NPK index for these three ratios, so we got n is the positive 93, for the 43, phosphorus is the -20, potash is the -23. So that means if you place all these index values in order of values, that is higher to lower side, 43 comes first, followed by the 20, followed by the 23. 43, whatever the positive value means, there is no deficiency. So here in this crop, there is no deficiency of the nitrogen in that particular crop. So the negative value shows the deficiency. Which is the more deficiency? The -23 is the K, and followed by the -20 is the phosphorus. So potash is the most deficient element. Of course, potash and phosphorus both are deficient, but comparatively, potash is the more deficient than the phosphorus. So the order of preference of the nutrients which are deficient also will get from the DRS. So how to interpret? The value of each function is added to the subtotal of one index and subtracted from the another. Just now I told you that minus value assignment and plus value assignment. For example, the value function of A by B is added to the A index and it is subtracted from the B index. I told you, for calculation of the A index, we'll take it as a positive. If for the calculation of the B index, we'll assign the negative value. So like that. Before the final ponderation, all the indexes are balanced around 0. Consequently, the sum of the nutritional indexes must be 0. When the results are negative, that lower than 0, that means deficiency. If the more the negative the index, the higher the deficiency will be in relation to the other diagnosed nutrients. Just I already explained in the last slide. On the other hand, high index values, the more the positive distant from the 0 indexes indicate the excessive quality of the considered nutrient relatively to the others. The more the positive is, the more the excess, or sometimes more may be toxic also. So these are the indices interpretation. For example, nutrient index. These are the arrived for some for taking into consideration of the 3 and 5 elements. For example, we have taken 5 elements analyzed for the plant samples, nitrogen, phosphorus, potash, calcium, magnesium. We have derived the DRS norms taking into consideration of the high yielding population. Then taking in those norms, we have calculated the index. For example, finally, the arrived DRS index values are like that. For example, we have to arrange from most negative to the most positive. The most negative -21 is, for example, nitrogen. Phosphorus 0, +7 is potash, +7 is calcium, +7 is magnesium. So all these nutrients are we should ignore. All these are the sufficient quantities. So the only phosphorus is the deficient, nitrogen is the deficient, because it shows the negative value. So it can be concluded from this index value that nitrogen index will to indicate the most deficient nutrient and compared to the other nutrients, other nutrient index values. So, and would probably the most limiting nutrient if the yields are entirely related to the nutrition. So, and the P index is equal to 0. That means it indicates the nutrient relatively less abundant, but less abundant than the other nutrients like potash, calcium, and magnesium. These are less abundant and would be the second most deficient nutrient element in the diagnosis. So, the recommendations for this diagnosis would be the addition of nitrogen and addition of phosphorus in small quantities is recommended to take care of this deficient nutrient elements. So one case study I will show that with examples. So this is the diagnosis of yield limiting nutrients in chili crop. This is one experiment was taken by the one of the PhD scholar who has worked under me and the Professor Jayashankar Telangana State Agriculture University. So Sri Jayasee is assistant professor. He is now associate professor in the university. So the main objective is the chili crop that this work which we have taken in the this southern Telangana zone consists of the Warangal district only and Medak district. So to find out the nutrient status of the soils and plants, so we found out what is the nutritional status of the chili growing areas of in this district. Also we have we have derived the critical nutrient concentration and we have refined with critical nutrient concentrations. We identified what are the and percentage of the particular nutrients, and later on we have developed the DRS norms and indices finally, and we have made it the order of the priority which nutrients are more required, and then finally we have tested the values. So these are the fertilizers, the commonly the fertilizer farmers were using in this area. So nitrogen they use it to apply ranging from 112 to 515 kg per hectare. Then phosphorus 54 to 285 kg, potash 35 to 150 kg, zinc 25 to 50 kg. So this is the data we have collected from the farmers and tabulated, and these are the ranges. The organic manures only 20% of the farmers are applying the organic manures. The majority of the farmers are not applying the organic manures. The yield of the chili crops in this region range from the 2050 kg per hectare to 8300 kg per hectare. It depends upon the fertilizer application and the soil type and different climatic conditions. So these we have formulated into different that range, mean, low, medium, and high. So generally the pH values are they are it ranges from 5.6 to 8.38 values of the soils. So mainly the 13 out of the 13%, 13 samples were slightly acidic, and 118 samples were the neutral. Neutral. 49 samples were the slightly alkaline, and 45 were the moderately alkaline. We have divided depend upon the status of the pH. So electrical conductivity, where it was the mean value was the 0.176, it was almost normal, and organic carbon it was very low. Organic carbon values we observed in the soils. 43% either were low or 53% were medium. So overall the 94% were the samples ranged from the low to medium. Only 7% of the samples were having high organic carbon. So nitrogen it ranges from 82% of the samples were deficient in nitrogen. Only 18% of the samples were medium. So no samples were high in the nitrogen content. Phosphorus in the soils ranged from 15 to 186 kg per hectare, and 63 samples were this is the mean value of the phosphorus, and 32% of the samples were having low phosphorus, and 69% of the samples were the medium, and 124 samples were the high content. So the most of the, if you see, observe the 124, 55%, more than 50% of the samples were sufficient in the phosphorus, soil available phosphorus content. So similarly, the potash content, 93% of the soil samples were having the sufficient amounts of the potash. Like the zinc, this is the zinc most important micronutrient element. The deficiency is observed in different crops. Here you see the 53% of the soil samples collected in this region were deficient in the zinc. So these are the nutrient composition ranges of the index leaves. Then we have to collect the soil data we have explained. Now coming to the analysis of the leaf samples, we have to collect the leaf samples as prescribed by the standard method. Reference values are there. At which stage we have to collect the sample, and which plant part we have to collect the samples. It depend upon the crop, it varies. So accordingly, we have collected the leaf samples from the chili crop and analyzed for the different nutrients. The nitrogen percentage, it ranged from the 0.59% to 6.9%. The mean value is 2.97%. Phosphorus mean value is 0.407%. Potash is the 2.92%. And zinc is the 10.56 ppm, that is mg per kg, to the 71.36 ppm. The mean content was 34.72 ppm. Like that, copper was mean content, it ranges from 10 to 56.57, and mean value was 2.87, and iron mean value was 104.56, manganese mean value was 8.464. So all these copper, iron and manganese were above the critical levels. They are in sufficient quantities. Only the zinc content is deficient. So yields, it ranged from the, as I told you, 2050 kg to 8300 kg, with the mean value of 5300 kg per hectare. So there are the different reference values developed by the different authors. For example, Kaminwar in 1993, he has developed, these are the critical nutrient concentrations. So this is 3.5 for nitrogen, 0.38 for phosphorus, 3.5 for potash. That means if nitrogen content in the leaf samples, if it is below the 3.5, it is the deficient. If it is above the 3.5, it is sufficient. Like that, these are the reference values taken. So the Tandon is the most, very famous scientist. He has developed, he has published a book. It contained reference levels and which plant part has to be taken for the sampling. What are the reference level? He has collected the total information from the country, and he has, given in his book, Tandon. In this book, we can see the different reference levels and different plant parts which have to be collected. So here he has given these three: the nitrogen for reference limit, critical nutrient concentration, and CNC for phosphorus 0.3, CNC for potash 2.5. So like that, and others also they give. And here the zinc we have given, that is 25 to 80 as the level, reference level it has given 38.9. Some other is given. So taking into consideration of the different reference values, that is one thing. So depending upon this, we will divide the population. Yield. Leaf samples, and that different farmers' crops, either it is deficient or sufficient, based on the critical nutrient concentration and sufficiency range. That also we have done at first before developing the DRS norms and indices. So then what we have done, we have to collect the yield data of the different farmers. For example, suppose 250 farmers we have selected, 225 farmers we have selected for the chili crop, chili growing farmers we have selected 225 farmers. So we have collected the information from the 225 farmers. So what is the chili data they got in the previous years? So based on the previous year's yield data, we have divided the population into low yielders and high yielders. So then how to divide the low yielders and high yielders? What is the criteria we have to take for dividing the population? Here this Nageshwara 1983, and is the famous statistician, he has developed one method, so that is the third quartile method. So it is used in our studies to demarcate, to divide the yield, the population into high yielders and low yielders. Here the third quartile method we are followed, that is nothing but n by fourth value. Suppose n is the total number of observation divided by fourth value. That value gives if the values are arranged after in descending order, where nitrogen is the number of observations. Suppose all the values we have to arrange in the descending order, then the n by fourth value we have to calculate. For example, third quartile, we have our population is 225 population, Chilli population, Chilli farmers data, 225 spots we have collected. So that means 225 by 4, this is n by 4 means 225 by 4. It comes to 56.25th value, 56.25. Then 56.25 value means 56th value. So suppose we have arranged in descending order. If we count from upper side, what is the value of the 56th number? The 56th number value minus 0.25 into 56th number value minus 57th value, it gives the actual demarcating value. So here the entire population was divided, based on this value, our entire population was divided into 56 high yielders and 169 low yielders based on the dividing yield level 6,315 kg per hectare obtained with the method. This method we obtained the value by calculating like that. The 56th value, 0.250 value, we have calculated like that. That value we got from the yield population 6,315. So the values, the samples which are having more than 6,315 kg per hectare are yielders, and below 6,315 kg per hectare called considered as the low yielders. So like that we have divided the entire population into low yielders and high yielders following the third quartile method developed by the Nageshwar Rao. So then after dividing the, just I told you the 56 number populations are high yielding population and 169 populations are low yielding population. Then what we have done, the 56 population, the nitrogen values of the leaf samples, we have calculated the mean values of these 56 samples. So suppose the nitrogen mean value of this 56 sample is 3.17 and phosphorus mean value of this 56 population is 0.42. K mean value of this 56 population is 3.13. So like that, all these mean values are of high yielding population. All these mean values of N, P, K, zinc, copper, and manganese, all these mean values are of high yielding population means. Then coming to low yielding population, we have taken the average of 169 population values. So these are the values: 2.89 for nitrogen, 0.41 phosphorus, 2.86 for potash, 34.17 zinc. These are the mean values of the nitrogen, phosphorus, potash, zinc, copper, and iron, manganese for the low yielding population values. Then selection of the form, how to select the expression of the forms. Those forms are called as the DIS norms. The values of that forms are called the DIS norms. So for example, ratios and products of nutrient concentrations were calculated in all possible combinations for the selected 4 nutrients. For example, here in Chilli experiment, we have taken nitrogen, phosphorus, potash, and zinc value because chilli is the the important crop in which we mainly will get the nitrogen and potash and zinc are the most important. These 4 nutrients are most important. We have taken into consideration, we have tested for these 4 nutrients in the chili crop. So the forms of expression for these selected 4 nutrients, this N, P, K and zinc these are the possible combination. For example, we take N by P, NP for example, we take NP. So N by P is the 1 ratio and reverse P by N is the 1 ratio and nitrogen in phosphorus is the 1 ratio. For these 3 combinations for the NP, then we will go for NK and N by K is the 1 ratio, K by reverse N by K by N is the 1 ratio and multiplication is 1 ratio. So like that N in relation to zinc will take N by zinc and reverse zinc by N and N by N into zinc. So like that. Similarly, this is for nitrogen relation in relation to phosphorus, potash and zinc. These are the ratios. Now next element is phosphorus. Phosphorus in relation to the potash again we will calculate. So phosphorus by potash and potash is the reverse of the K by P and multiplication product P and K. And similarly for P and zinc, P by zinc, zinc by P and P and zinc. So this is the P zinc combinations. Then coming to K, then K by zinc, zinc by K and K into zinc. So these are all these possible combinations of the nutrient ratios derived from these 4 selected nutrients under testing. So the means, variance, and coefficient of variations of the various forms of expressions are calculated. These are these ratios, these possible combination ratios. We calculate the mean values. So these are the test samples. These mean values will calculate, and coefficient of variations also will calculate, variance also will calculate all these ratios. So then, how to select? For example, we take into consideration. For example, we take into consideration NP. For example, NP combinations, what are there? N by P, P by N, and N and P. So, with respect to the N and P, these are three are the possible combinations: N by P, P by N, and N and P. So, among these three combinations, we have to select the one combination only. So nitrogen phosphorus combinations, among three combinations, we have selected one combination only. So like that, nitrogen potash combinations, three combinations. Among these three combinations, we have to select the one combination only. So how to select this combination of that nutrient ratio is here we can see. For example, we take nitrogen phosphorus combination. One is the nitrogen and phosphorus product, nitrogen by phosphorus, and reverse phosphorus by nitrogen. These three possible ratios for the nitrogen and phosphorus. So for here, for these ratios, we'll see this low yielding, these mean values of N and P from the low yielding population is 1.07. N and P of the high yielding population is 1. Okay. So then what we have done, then the coefficient of variations of this particular value, that particular ratio is 35.9. And the coefficient of variance is 0.15. So similarly for nitrogen phosphorus product, mean value is 1 and coefficient of variation is 25.9, variance ratio is 0.07. So here the variance ratios we will calculate. That is variance ratio of the low yielding population divided by the variance ratio of the high yielding population. That is 0.15 by 0.07. It gives to 2.18 variance ratio of that particular NNP. Similarly, by N by P, the mean value from the low yielding population is 7.44. The corresponding CV and variance values are 29.7 and 4.89. So similarly, the N by P values, mean values for the high yielding population is 7.75. Respect to C and coefficient of variance and variance values are 29.3, 5.15. So here that variance ratio of the low yielding population divided by the variance ratio of the high yielding population, that is 4.89 divided by 5.15, we get the 0.95. So similarly for phosphorus by nitrogen combination, these are the mean values of the low yielding population. This is the mean value of the high yielding population. Similarly, we calculate the variance ratio. Here we got variance ratio P by N is 8.92. So these are the variance ratios for these combinations of the nitrogen and phosphorus. So here which is the highest variance ratio? This is the 8.92 is the highest variance ratio. So that means the nutrient ratio which is containing highest variance ratio is selected as the form of expression. So here among these three combinations, phosphorus by nitrogen is selected form of the expression. This phosphorus and nutrition nitrogen ratio is selected among these three combination. So then what is the mean value of P by N in high yielding population? The P by N mean value in the high yielding population. The mean value of the selected expression, the expression we selected is P by N. So what is the mean value from the high yielding population is the 0.13. So the 0.13 is called the DRIS norm. 0.13 is called the DRIS norm. That is called the DRIS norm, which we will take into consideration for calculating the DRIS indices. So these are the selected forms of expression. Here I have shown for the NP combination one selection. Like that, we will select for the different combination. Among the PN combination, P by N selected, and N and K combinations, we have selected K by N. And zinc, among the N and zinc, we have selected zinc by N. Among the K phosphorus, K by like that for this all the 5 elements. These are the 6 combinations we have selected from the, taking into consideration of the coefficient of variance ratios. So these are the mean values. So here what happened, these are the selected expressions. So So these are the selected expressions. The mean value of these expressions, the mean values of the yielding population. For example, the selected expression P by N mean value is 0.13. So this is the DRIS norm value for the P by N. Like that, similarly for the selected expression K by N, the DRIS, this mean value of the yielding population 1. This is called the DRIS norm value for K by N. So similarly, the selected expression is the zinc by N. For these two combinations, the mean value of the yielding population for this particular ratio is 10.024. So this norm for zinc by N is 10.24. Like that, similarly for all other ratios, all these main values are considered as the this norm values for these selected forms of expression. This is mainly followed by the depend upon the variance ratio. So then we have to calculate then now the first step what we have done, we have arrived all the selected forms of expressions, and the mean values of the yielding population for the selected forms of expressions are called DRIS norms. Then taking into DRIS norms, we have to calculate the index. This is the next step. For example, A index, just this is example I have shown. So A index means for a year A by B, function of A by B, function of A by C, function of A by D, function of A by D. This is N is the number of elements. It may be 2, 3, 4, it extend like that. So then if the function of A by B, this is capital A by B, capital A by B is the test value, and small a by b is the reference value. That is, small a by b is nothing but the DRIS norm. Earlier slides what we have shown the mean values of the yielding population for the selected expression value, that is called reference value, DRIS norm, small a by b. So capital A by B is the test value sample. If test value ratio A by B is the more than or equal to small a by b, then we have to use this formula. Then function A by is equal to capital A by B, that is test population ratio, divided by reference value ratio minus 1 into 1000 by the coefficient of CV variation. So if the test value sample is less than reference value, then this equation we have to follow. Function A by B is equal to 1 minus small a by b. This is reference value divided by the test value into 1000 by CV value. Using these values depend upon the test value samples with reference to value, with reference to the this norm values, we have to select the calculation. For example, if it is for nitrogen index, we are calculating for the nitrogen, phosphorus, zinc. For example, this is function value of N by P, N by K, N by zinc. How to calculate? If the test sample N by P is more than small N P, that is reference value, we use this equation. If it is less than reference value, we use this equation. So instead of A, just here I have shown for the nitrogen phosphorus ratios. Then we will take one example of the one leaf sample data and how we will calculate, we will show. For example, one field sample, we have collected the leaf samples in the plot. It showed nitrogen 2.18, phosphorus 0.5, potash 2.86, zinc 43.59. These are the 4 elements we have tested in chili crop. So what are the forms of expression? Forms of expression, for example, for nitrogen, nitrogen P by N, K by N, G by N, these are the selected forms of expressions. Selected forms of expression. Earlier slide I have shown. Here you see. So these are the selected forms of expression I have showed. So those things here. So these are the selected forms of so these are the selected forms of the expression P by N, K by N, and zinc by N. The values of these ratios, the selected expression, the values of the yielding populations with respect to these ratios are called DRIS norms. For example, P by N. P by N, what is the P here? Test sample value 0.5. Okay, 0.5. And test sample value of nitrogen here is 2.18. So 0.5 by divided by 2.18, the P by N value is 0.229. This is the ratio value of the test sample. Capital letters means test sample. Then coming to the, already we have derived the this norm value for example P by N. Earlier slide we have shown P by N. Here you see P by N. P by N, what is the mean value? 0.13. The P by N selected expression, the mean value of the yielding population is 0.13. So that means here P by N is 0.13. We have taken this test sample. So then 1000 by C, the coefficient of variation related to this small b by n, related to this small b by n. You see, small p by n, this coefficient of variation is 18.2. So 1000 divided by 18.2, it gives the 54.9275. So like that, K by N also. These are the test sample values. This is the reference values, this norm values. And calculated 1000 by coefficient of variation will less. So from these values, where P by N, K by N and zinc by N are the test samples, mean leaf composition, and small p by n, k n, small zinc are the mean leaf composition of the high yielding population. I told you these are the reference. CV is the coefficient variation of the high yielding values. So then we will calculate the nitrogen index. Nitrogen index. So here the selected forms of expression here is P by N. Okay, P by N. Here P by N. And next one is the K by N. Here K by N. Next one is the Zn by N. Here the Zn by N. These are the selected norms. So when how we will assign minus value and plus value? For example, we are calculating nitrogen index. Nitrogen is in the lower position, that is P by N. If it is the lower position, then we have to give the minus value. Here also it is lower position, we have to give the minus. If here also lower, the minus. If it is upper side, we have to give the plus value. Depending upon their position, either is a denominator or nominator, then we have to assign the values. So what are the selected ratios? 3 ratios. So divided by 3. So like that we will calculate the nitrogen index. So here you see, so functional values first we have to calculate. So if the test sample value is more than reference value, this is the type of calculation. If the test value is less than reference value, this is the type of calculation. Here what happened, because the value of the PN, this is test sample. Here the value of the test sample is here 2.229. Okay, and reference sample is 0.1327. That means the test sample value is more than reference sample value. So if the test sample value is more than reference value, this formula we have to take. This formula we have to take, this P by N by small p by N into -1 into 1000 by CV. So because the value of the test sample is less than reference, this norm value. So this we have substituted all the values and we got 39.8608 is the functional value of the P by N. So like that we have to calculate the functional values. Like that we have to calculate the functional values of these all values. We have to functional values of these functional values of n by p, n by p, n by p. Like that for all these functional values we have to calculate. Then here the function of Pn we got 39.86. Likewise, function K by N and functional value of zinc by N will be calculated. Those are calculated 11.9, 22.7. Similar type of calculation we have done. We arrived for these ratios 11.91 and 22.92. So the nitrogen index, just now I showed that. Then we have to calculate here we have calculated the functional values, function of P by N, function of Kn, function of Zn by N. Then we have to substitute the functional values in this equation. Calculate the particular nutrient index. For example, nitrogen index, the functional value of the P by N, functional value of K by N, functional value of the Z by N. All here, all these ratios, nitrogen in the lower side. That means for all the ratios, functional values, we have to assign the minus values. So here we have assigned the minus values. The number of observations are 3 divided by 3. So we have substituted all these values P by N, K by N, Z by N in this. So finally we got to minus 24.83. This is the nitrogen index value, 0.24.83. So the manually calculated value is the 24.85. So, okay. So the nitrogen index obtained using the computer program. So this for all these statistical calculations, we have developed one software in the computer center of the Professor Jaishankar, Telangana State Agriculture University. I was the main person behind taken help of the computer, scientist, principal scientist computers. Then we have developed one software program. If we feed the nutritional values, directly will get the nitrogen index values. Like that, we have developed the program. So whatever the calculation, the index nitrogen we got from the computer-based program is same as we manually calculated. That means the whatever the computer program developed was sound enough. It is valid. Similarly, the indices of P, K, and G should be calculated and can be put in order of priority depending upon their index values. So similarly, for all for like nitrogen index, we have calculated phosphorus index, potash index, and zinc index because four elements we studied. So phosphorus index we got plus 19.98, potash index minus 1.346, zinc index plus 11.16. So here among all these four nutrients, the more minus value, more the negative value, that is 24.85, the more negative value, that is nitrogen is deficient, and another minus value, that is potash. This is the potential difference. So among the four elements, nitrogen and potash are the deficient elements, and among these three elements, we can prioritize. This is more negative with the nitrogen. So nitrogen is more deficient than potash. We compare these two. So that means nitrogen is more than K deficient. So here in DRIS, the main advantage is not only diagnosing the nutrient deficiencies, we also can prioritize which nutrient is more deficient when compared to the other nutrient deficient. So these are the DRIS indices and order of nutrient requirement for chili fields of the Warangal district. Some of the, some of the plots we have given, for example. So these are the index values: nitrogen index value, phosphorus, potash, and zinc. For example, here the first plot, for example, one farmer play a plot. Here the more negative, we have arranged in the, here more negative value is for nitrogen. So that means all P and K, zinc are positive values. So for this plot, the nitrogen is the only nutrient deficient. For example, second field will go here also nitrogen minus 28 and phosphorus positive, potash minus, and zinc positive. So potash is positive, but more than potash, the nitrogen is more deficient because minus 28 is more, most negative. So the nitrogen is most deficient, followed by the potash. So N greater than potash. So nitrogen is more deficient, followed by the potash. Similarly, we have to go to third plot. Third plot, here we got phosphorus negative value, potash negative value. The more negative value is for potash, followed by the phosphorus. So that means the potash is more deficient than the phosphorus. So here we indicate the order of nutrients. Only deficient nutrients will indicate, and the order of the deficiency also we can arrive from this calculation. Like that, for all the plants, we have calculated the order of nutrient requirement for all the farmers, that is 225 farmers. So these 225 farmers, 225 plants, we have 225 fields. We have analyzed, we have divided based on the critical nutrient concentration value and we have the DRS values. We have compared both samples deficient through critical nutrient concentration and samples deficient through DRS values. So here among the 225 fields, so when we follow the critical nutrient concentration, only 16 fields were the deficient in nitrogen, and that is 7% of the fields were the only deficient in nitrogen. But when we follow the DRIS, out of 225 samples, 111 samples were deficient in nitrogen, and 49%, 119 samples were deficient. That comes to the 49% of the samples were the deficient. So what we observe here, even if we observe the less percentage of the nutrients deficiency through the CNC, we are applying more nutrients, means that is the hidden anger of the particular nutrient is there, which is restricting the yield. Even though we may not get the symptoms on the field, we are the yields are restricted because of the hidden anger of that particular nutrient. So the DRS will take care of the all nutrients in ratios in relation to the other nutrients. It will give the correct figure of the diagnosis of the nutrients in the crops. So like that, phosphorus among the 225 fields, through CNC only 11% samples were deficient. When we go to DRS, 108 samples were deficient. So then for potash, 42 samples were deficient through CNC, and 121 samples were deficient 3 DRS. So here when we compare, but whereas for zinc, we follow the CNC 165 samples were deficient when coming to DRS, comparatively less number samples, 102 means CNC 73% for samples were deficient, but whereas for this 45 samples for this gives the correct figure. Though here overall when we compare the sample, I mean popular deficient with through CNC and DRS through DRS we are noticing the more percentage of the samples deficient. So then there is a method developed by the Bhargava and Sumner to calculate the what are the I mean values, that is what is the value of the deficient range and low range, sufficient range, high range, and excessive and toxic range. So five ranges we have calculated. For that one formulas they are derived. The range of sufficiencies or values derived from the mean value of the 4 by 3 standard deviation and mean value of the plus or minus 8.3 standard deviation respectively. So this is the value derived from this between these two are called the sufficiency values. Then the values of nutrients between the less than mean minus 8.3 CD are considered as deficient. Whereas the low range included all values between the more than mean minus 8.3 standard deviation and less than mean minus 4.3. These between these values are considered low range. So like that, for sufficient, the more than mean minus 4 by 3 SD and less than mean plus 4.3 SD, these are in between these are called sufficient. Whereas the range between the more than mean plus 4.3 SD and less than mean plus 8.3 SD are expressed as the high. So the nutrient concentration more than mean plus 8.3 SD or expressed or defined as the excessive or toxic. Like that, we can arrive the values for the particular crops as a low values, deficient is sufficient, leave, high, and excess. Like that, we can categorize. So, following those calculations, we have derived sufficiency ranges of nutrients from the DRS technique for the nutrient density survey of the Chilli for the Warangal district. We have calculated like that. We have derived these values the nitrogen, phosphorus, and potash. When if you see if nitrogen percentage in the leaf sample is less than 1.1%, it is called low. And when it ranges from 1.1 to 2.0 to call it is optimum. So this is the optimum value for getting the optimum yield. So when it ranges from the 2.0 to 3.9, it is high. If it is more than 3.9 nitrogen value, it is excess. So like that, we have categorized for the phosphorus also. Less than 0.17 is the low. For potash, less than 1.45% is the low. Like that, zinc less than 12.9 ppm, it is the deficient. So like that, we have categorized these low values. So these are the reference values below which these values are called deficient in those particular nutrients. So finally, what we conclude, the nutrient diagnosis with the DRS is more better and accurate than the critical nutrient concentration. So here through DRS, more number of nutrients are identified as the yield nutrient. For example, critical nutrient concentration, for example, 2-3 elements, for example, diagnosis. Whereas for this, we may identify more than that. So more number of nutrients, there is a possibility of diagnosing as yield limiting nutrients because it will take into consideration of the hidden hunger of the nutrients in the plants. So this identifies and prioritizes the yield limiting nutrients in order of their requirement to collect the most required nutrient, thereby getting the increased pod yield in chili. So not only these, it identify the what are the nutrients limiting the yield. So order of preference, this order of the limiting nutrients also it gives. So the more the deficiency nutrient, we can take up the application of that particular nutrient immediately. We can give preference depend upon the prioritizing the deficient nutrients through the DRS. So then whatever the values, these DRIS norms and DRIS indices, whatever we have developed for chili crops, whether these are correct or not, the validation is required. For the validation of these DRS norms, we have conducted one experiment, field experiment here with different doses of the nutrient. Nitrogen, we have taken control, and what is one is the 100% recommended dose, and another is 50% more recommended dose, and another is the double of the recommended dose. Like that, we have selected different levels of the nitrogen, potassium, phosphorus, and we have tested in the chili crop through the field experiment. So these are the 12 combinations of the treatments. This is the control plot. This is control of nitrogen in combination with potash control, potash 100, potash 150. So like that, 100% that is recommended dose nitrogen in combination with 0 potash, 100%, 100 potash, and 150 potash. Like that, 150 nitrogen with this. So different, all possible combinations, 12 combinations we have selected for the field testing. So then, if we see the all the leaf composition, all these from 12 experiments, 12 treatmental combinations, we have collected the index leaf samples, analyzed for the nitrogen, phosphorus, and potash contents and zinc contents in the leaf samples taken from these different treatments. So then, what happened? These are the values arrived for the analysis. So then we calculating the DRIS indices and prioritizing the order. After calculation of the DRIS indices, in this, for example, this plot, we got nitrogen is the limiting and potash is also limiting. So, but nitrogen is most limiting. So then there we got, for example, 4,500 kg per hectare of the yield. So then what happened for next treatment? For example, you see, you read nitrogen is control. Here we increase the potash to the 100 kg. So when we increase the potash to 100 kg, what happens? The potash, which was the yield limiting nutrient in the first combination, then it has gone. Now potash is no limiting because here we applied potash. So that means it is reflecting good. The testing value it is reflecting good. So then yield is slightly increased. We have taken care of the potash limitation here. Then coming to the potash again, still we increase it to the 150 under zero nitrogen control. Here also the potash is no limiting because we increase the potash deficiency. So nitrogen is the only limiting. So the 5,000 kg increased yield we got. Then when we go to the 100% nitrogen recommendation, the potash is zero. So because the potash is zero, no potash applied, here it is showing the potash is the more deficient nutrient. So that means it is correctly reflecting the nutrient deficiencies that depend upon the manual fertilizer application, followed by the nitrogen. So even though the nitrogen recommended dose of nitrogen we are applying, still it is showing the nitrogen deficiency. That means so there is a possibility of getting increased yield when we increase the nitrogen from recommended dose to the little more increased dose. For example, 100 to 150 dose here you increased. So then what happened? The potash, this nitrogen limitation has gone and yield is increased. So that based on these fertilizer applications, the particular order of nutrient priority was corrected. And for example, for zinc here, you see the nitrogen 150 kg, that is 50% more than recommended dose, and potash is the recommended dose. Here the nitrogen and potash are we are giving more doses, but here no, we have not given zinc. What happened here? Zinc has become the limiting nutrient. So what happens in this particular like treatments where we get observed? So this type of plots we have to apply only zinc to get the more yield of the chilies. Like that. So whatever the DRIS norms and DRIS indices we have arrived for the chili crop when we tested in the field, it is showing the correct reflection on the testing. That means the whatever the values we developed or test from the test, these are the valid. These are the valid. So these are the main table we have given. This is, for example, the potash is zero. That means potash is showing deficient, and the potash recommended dose we applied. Potash deficiency is gone, and still we potash increases. There is no deficiency. And if we see the nitrogen control plot, no nitrogen. Nitrogen is showing deficient, and nitrogen recommended dose we applied. Still nitrogen is showing difference. But when increase the dose 50% more to the 150%, the nitrogen deficiency has gone and still increases the nitrogen. So that means the nitrogen, whatever we are giving to that crop, is not sufficient. We can increase the recommended dose of the nitrogen. This is the field crop view. So recommendations to DRIS, based on the DRIS approach, nitrogen, phosphorus, potash, and zinc deficiencies were observed in the crop are 49, 48, 54, and 45% respectively. And DRIS indices and critical nutrient concentrations are quite divergent. Both are giving different conclusions. So nutrient deficiency to critical nutrient concentration, there nitrogen, phosphorus, potash, and zinc only these deficiencies through CNC only we are showing 7.9 and 73% respectively. But whereas nutrient deficiency through DRS, this NPK and zinc deficient to an extent of 49, 49, 54 and 45% respectively. The more percentage of the deficiencies are shown through the DRS approach. So there is a superiority of the DRS approach over this critical nutrient concentration because it will take into the consideration of the hidden hunger of the nutrients in the crop. So comparatively, more number of fields are identified by the DRS than those identified by the critical nutrient concentration. Majority of the nutrients found deficient through critical nutrient concentration also find place as yield limiting by the DRS. Whatever the nutrient diagnosed deficient through the CNC are also find place found deficient in DRS. In addition to the particular nutrients identified by the CNC method, still more nutrients are identified through the DRS in addition to the CNC. So the nutrient diagnosed as limiting did not find place in the CNC. So some of the nutrients found deficient through the DRS, they found no place through the identified through critical nutrient concentration. So DRS is not only identifying the limiting nutrients and different nutrients, but also prioritize which is the most required nutrient. 1, 2, 3, 4. It prioritizes the required nutrients based on their requirements. It's not only limiting nutrient, it will show the order of the priority to get the more yields. So effectiveness of the DRIS in the field fertilizer factorial experiment in Chilli, it increased dose of limiting nutrient. The limitation was disappeared or changed from first place to second place by increasing yield and leaf nutrient composition. In last table, I have explained about this. So that from the table, what we can do, the recommended dose of nitrogen, that is 450 kg per hectare. These are the recommended dose. But there, by increasing the 150 dose, that means 300 to the actually recommended dose was 300. By increasing 50% more to the 450 kg per hectare, and phosphorus is the same as the recommended dose 60 kg, and potash as recommended dose 120 kg. Just increasing the 50% dose for nitrogen, and the recommended dose of zinc, we could get the increased yield. We could identify the nitrogen most deficient, and the whatever the recommended dose of nitrogen is there for chili crop which is not sufficient, we can increase still 50% more to recommend for chili crops to get the higher yield in this zone. So comparatively, more number of fields are identified as the DRS than the identified by CN. This already I have explained in the earlier this one. So then what happened? That is one field experiment just now I showed. In some of the farmers' fields, out of 225 fields, we have selected some few farmers' fields, and we have applied the fertilizer doses in those farmers' fields. For example, field number 30, one farmer, Bukya Lachana, for his name, farmer name, village in the some Dunakal Mandal. This is Divinisi case village. Here, 2013, when we have taken samples before calculation of the DRS norms and indices, when we took samples first time, he has applied 300 kg nitrogen, 130 kg phosphorus, 50 kg potash, and no zinc. So then what happened here, when we calculated the DRIS norms and indices, there we found the potash was the limiting nutrient in this particular field. What happened next year? What happened down? This is we found 2013, 2014 year. We went to that field based on the limiting nutrient potash. We applied the potash, increased the dose of the potash. Here potash was 50 earlier. We have here increased it 50 dose to the 65. So then what happened? This limiting nutrient has gone from the yield was increased from 6,360 to 6,740. So like that, similar different farmers fields across the zone we have tested. Another field, for example, this is another farmer. This is Raj Reddy. You see, Raj Reddy earlier before arriving at norms, he was applying 400 kg nitrogen, 100 kg phosphorus, no potash, and 25 kg zinc. Where because he got phosphorus as a deficient nutrient. Then next season when we applied phosphorus from increased from 100 to 125 increased, then the whatever the limiting nutrient potash has gone, it was rectified. Yield is also increased from 7,000. Yeah, yield is also increased from 6,580 to 7,100. So correcting the limiting nutrient, the yield is increased. So that means whatever the DRIS norms and indices we have developed found valid found valid. We have found valid through the field experiment as well as testing in the different farmers fields in the zone. So these are the from different fields we have tested. So nutrient diagnosis with the DRS is more better and accurate than critical nutrient concentration. More number of nutrients may be of hidden hunger were identified as the yield limiting nutrients. DRS identifies not only the limiting nutrient but also prioritizes the yield limiting nutrients in order of their requirement to correct the most required nutrient, thereby getting the increased yields in the chili. So then, so not only Chilli we have done, so the diagnosis and recommendation integrated system we have done for the different crops in the Professor Jaishankar Telangana State Agricultural University. I was the person involved in developing the DRS norms and indices for the different crops in the Telangana, even combined Andhra Pradesh state. I am the only scientist across the state and in the university within the combined AP state. I have developed DRIS norms and indices for the different crops in our regular experiments as well as I mean giving experiments to the PhD scholars. So like that we have developed the DRIS norms and indices for the mango. 2006 we have developed for mango. 2002 we have developed for sweet orange. 2008 we have developed for oil palm. 2012 we have developed for rice. 2016 we have developed for maize. 2016 same year we developed for cotton. 2016 we have developed for chili. So 1, 2, 3, 4, all 7 crops we have developed for DRIS indices and norms. These are available. So all these crops we can take leaf samples, that is some prescribed leaf samples, index leaf samples if we take from these crops and analyze for the nutrient composition and incorporate and feed the data in the developed software program. Finally, we can get the order of nutrient requirement, limiting nutrients requirement. Those nutrients we can apply to the crop and rectify the deficiencies, and we can get the increased yield of this respective crops. So among that developed decision norms, we have published the papers for mango, that is the communications in soil science and plant analysis. It is the popular journal in the world. It is Scopus journal, and other also, that is sunflower also we have published, sweet orange also we have published, and rice also we have published. Journal of the Indian Institute of Sciences. It is also reputed journal. And the progressive research also, that one for maize we have published, and for cotton also, that is one thesis submitted, and for chili also one thesis submitted, one of the crops my student. So all these are these different articles published in the journals. So I thank you very much for listening patiently. This is the complicated topic. It is not a routine topic on par with others, but it is a scientific topic. It is very much useful to the scientists, in particular to the soil scientists and agronomists, to utilize this developed software program, and we can arrive the deficient nutrients, not only deficient nutrients, in order of the nutrients requirement for the different crops, and we can apply those deficient nutrients, and finally we can get the increased yields. Thank you very much.